Okay, let's talk about the graph ADT. So there's a core set of command operations. I'm going to skip the typical ones that you see, like make empty and constructor and is full and those kind of things. The implementations in the book, they're fairly straightforward, and I think at this point you kind of understand how to do those kind of things. Talk about the main focus, which is the meat and bones operation. So add a vertex, add an edge, get weight, get two vertices, clear marks, mark vertex, and is marked. So add a vertex. Let's go through creating a simple graph here. So we got a simple graph. A goes to B, and A goes to D. B weight 1, and to D is weight 2. D goes to B with weight 3. B goes to C with weight 4. Now, when we want to add a vertex to create this graph, we have to add A. Then we add B, add C, add D. Boom, we've created 4 vertexes, but there's no weights in between them yet. So now we need to add edges. So add edge takes 2 vertices and a weight, optionally. It's best in the graph ADT implementation that you go ahead and implement it as always as a weight, and then if somebody wants to make an unweighted graph, then they basically just send in a weight of 0 or some marker. But that way the graph ADT supports both. So you'd say add edge A, D, 2 to add the edge, weight 2 with AD, add edge A, B, 1 to add edge, etc. Fairly straightforward. Sometimes you might want to get the weight in between 2 vertices, so that's get weight dB equals 3 should return integer, or whatever value you're using as weight, type of value. Let's see, get to vertices. Now get to vertices returns, this is a kind of funny name for the function, but basically will return a big list or data structure of some type of all the connections out of a vertex. And you're going to need this, as you'll see in graph traversal algorithms, to do anything with a graph. So at any point, we're going to look at a node, and we're going to want to know the edges that come out of it. So for example, get to vertices of A will return the set of vertices from A to D, or sorry, the set of edges, I'm sorry, not vertices, set of edges from A to D and A to B. So we'll return the edge A, D2 and A, B1. So how does it do that? Because it's a complex data structure. Well, your book does it with a queue, and that's generally a good way to do it. You can do it with any data structure you want. A queue makes sense because it allows simple NQ, DQ, or push pop, basically, it's not push pop because it's stacked, NQ, DQ operations in order 1 time, so very quickly to just be able to pull out items. And usually what you're doing in a graph traversal algorithm is okay, I need the first edge that's connected. Okay, now I need the second edge. Now I need the third edge. So a queue is a natural operation for doing that, so that's why they use a queue, because it serves a good purpose. So you return a queue of the edges, which is the A, D, and the 2 in between them, to the caller, so that they can then operate on it. And we'll go further with that once we talk about graph traversal algorithms. The next 3 are marks. And again, you have to suspend belief a little here, because I'm telling you you're going to need them, that they need to be implemented because they'll become useful for graph traversal. So when you're looking through traversing a graph, you look at the node A, now you get vertices for D and B, but you might want to know, okay, well, did I already look at one of these? Because maybe there's a cycle or a loop, as in this case. You went to A to B, and now you end up at D for some reason, and D says go back to B. You're going to want to know if you visited B, and so that's what is marked is, or is visited. Sometimes it's called either one. And then mark allows you to mark it so you know that you have visited it, so that if you call is visited, it will return true. So these are really just data tracking devices for you. They are very easy to implement because of that, but they're important for a lot of algorithms, so they're part of the ADT. And of course, clear marks resets everything for the next purpose. So now let's talk about underneath all this, the ways to represent edges and vertices as a data structure. So there's 2 ways to do this, and they both have trade-offs, of course. So first, an adjacency list, which is what we have up here. Adjacency list is basically a linked list analogy, where you keep an array of the vertices. So in this case, we have 4 vertices, A, B, C, D, so we make an array of 4 positions, A, B, C, D, 0, 1, 2, 3. And then we create a linked list where the linked list nodes are a complex data structure, not just has the next, but also contains the node and the weight. So the first linked list structure for A, for example, would be this B node. So A links to a node, and you use an integer here to point back to the array. So B is in array position 1, so the node that is in this first data structure is 1, and then the weight is from the weight of the graph is 1. So A A's root goes to a linked list structure with 1, 1, and then the next points to another linked list structure with 3 as the node for D down here, and 2 is the weight. And this way you can store an infinite number of edges out of each in particular vertex. And this goes on for B and D as we see here. So B will have a node, linked list node with 2 and 4, and D with 1 and 3, and C with nothing, because C doesn't have any edges coming out of it. You can also do this with a matrix style, stay on this side, a matrix style representation called adjacency matrix. And this gives the matrix version of the same numbers. So instead now, doing a linked list, we're doing an array. So now we locate a 4 by 4 array. So 0, 1, 2, 3. And of course we still have to keep the nodes in a basic array, A, B, C, D. But now we create a 4 by 4 array, and we simply put numbers at the intersections between them. So let me give you an example. So A is this is array index single dimension 0, and then the second dimension 1, and the second dimension refers to the pointer back to the array itself. So 1 here refers to B. So in the table A and B, which is 1 here, which is the weight. And then in the table again here, if you go across the row of B, intersect it with 2, which is C, we want the weight 4, so 4 should be there, as it is. And then again, cross A down to C, A to D, which is the third position, is a 2. So it's a little hokey explanation to think about, but it's simply reading a table across, basically, where you have the table positions of the two nodes, the first one and the second one as the first index and the second index down. So this is a really easy, nice implementation for that reason. But notice a problem, particularly in this graph. We have 1, 2, 3, 4 weights, but now we have 16 memory spaces allocated. So we just wasted 12 memory spaces. So this is a huge memory hog, depending on the graph. I mean, if the graph is fully connected and complete, basically, then you don't need to worry about the space, because all these edges are going to be filled anyway. But in a sparse graph like this one that we've created, it's a big waste of space. Whereas the linked list structure up here doesn't have that problem. We only create a node, a linked list node, for when there is an edge. And if there isn't an edge, we don't create a node. So you remember this problem. We studied it back in earlier weeks. This is the linked list versus array, space versus time trade-off, and all the other problems exist too. When you insert here, you have to insert is quick, but linked list insert is quick, but with an array 2 by 2 matrix like this, if you add a whole another vertex, for example, this is difficult, because now you have to recreate the whole array and add another row to it. If you delete a vertex again, this messes everything up. So huge runtime problems with arrays, the same ones that existed, with adjacency matrices, the same ones that existed back with arrays, and we studied back in lists for messing with the graph itself, whereas linked list doesn't have that problem, and space has this problem here. But this is faster to access a particular edge node, right? So if A has 20 edges, you're going to have to search down that linked list to find it, whereas it's very easy here to just go A, D, boom, and it's right there. So quick access here, slower access there, and same trade-offs that used to exist, so you're familiar with them, I'm sure. And so that's it for graph ADT. Now we're going to take this, actually next week, and we're going to use this to create some graph traversals that are very interesting. So stay tuned for that. But this week we're also going to talk about breadth first and depth first search, which is another simple graph traversal.